Hi, welcome back to this channel. In this video, we're going to discuss about the question on the haloalkane based on this few learning objective. Tutorial question number 6. Outline the synthesis of following compound from propanol, which consists of 3 carbon, and then because there's no number in the name of the alcohol, so we will consider it is 1 propanol, and then going to produce 1,2-dibromo propane, so CH2 CH3. Okay, so as we know, alcohol, in chapter alkene we heard about alcohol, so at where it will undergo dehydration with the presence of concentrated sulfuric acid with heat, and then will produce alkene. So alkene can produce dihaloalkane by reacting with bromine in CH2Cl2 in the dark. So this is the answer for question A. Now let's proceed to question B. From the cyclopentene and then produce chlorocyclopentane. So for this one, it will be very simple. We can just add HCl and then break the bond, because there is both carbon have 2 hydrogen, so we no need to consider the Markovnikov rule, so we can just add in Cl. Or you have another way. From the cyclopentene, you react with the hydrogen with the presence of platinum to produce the cyclopentane, and then the cyclopentane will undergo halogenation with the Cl2 in CH2Cl2 with the presence of UV. So since this question is not specific how many steps, so you can choose either 1 step. This one will consider as 1 step synthesis, or you also can consider as 2 steps through the hydrogenation and then halogenation. Okay, let's continue with tutorial question number 8. Show the outline synthesis from of the following compound. Ethane to 2-methyl-2-butanol. So from here we will notice ethane has 2 carbon, while 2-methyl-butanol, methyl 1 carbon, butanol 4 carbon, total is 5 carbon. So from 2 carbon to 5 carbons, this one is not in, no, we haven't discussed yet, so we will discuss in the next subtopic, which is in the Grignard reagent. So we will ignore question 8a. Then let's proceed to question B. CH3, CH2, CH3, Cn from propane. So propane have 3 carbon with a double bond. CH3, CH, CH2. Then again, from 3 carbon, and then the product will become 1, 2, 3, and 4 carbon. Normally, when you have extra 1 electron, we will relate with the KCN. Once relate with the KCN, we have to relate with the haloalkane. So means that the alkene here will react with the haloalkane to form the alkane will react with HX to produce haloalkane. Okay. However, at the same time, we notice that if we use HS only, the product of the haloalkane produced will be CH3, CH halogen, and then CH3, because we want to produce the haloalkane based on the Markovnikov rules. Okay. However, when we look at the structure of the CH3CH2CN, the halogen supposedly is at the terminal of the carbon, so that the halogen, once replaced with the CN, it will be straight chain. But this one, if the halogen replaced with the CN, it will become a branch structure. So with this, we know that Markovnikov is not obeyed in this synthesis pathway. So means that we are going to use anti-Markovnikov rules. Okay, so if we use anti-Markovnikov rules, from what we already know, there is only one process in our syllabus that is follow the anti-Markovnikov rules, where we are going to use HBr with the presence of peroxide H2O2. So we will become CH3CH, break the double bond, form two new single bond. So because of anti-Markovnikov rules, so the hydrogen will attach to the carbon with less hydrogen. The nucleophile will attach to the carbon with more hydrogen. Okay, then next formula we react the haloalkane with the KCl with the presence of ethanol reflux. So once this happens, okay, sorry, basically we have to draw like this. So CH3, CH2, CH2, the Br will replace with the Cn. So we produce the structure as requested in question D. Okay, now we proceed to 8C, 2 mole of ethanoic acid from 1 mole of 2-bromobutane. So 2-bromobutane from 4 carbon, and then become the ethanoic acid is 2 carbon. So when the number of carbon decreasing, so basically we will relate to the ozonolysis. So when we relate with the ozonolysis, we need to relate with the alkene. Okay, so now we have the CH3, CH, CH2, CH3. So haloalkane, if we want to form alkene, we are going to undergo dehydrohalogenation, at where we need the KOH in ethanol, heat to produce the CH3CH double bond CH3, so that we will able to obey the Sagev rules to get the major product. Okay, then next undergo ozonolysis. However, if we look at here, ozonolysis only will add the oxygen next to double bond. Okay, but here will produce oleic acid, carboxylic acid. So means that we are going to react, the alkene will react with the strong oxidizing agent, so that it can undergo further oxidation. Therefore, in this case, the alkene will react with KMN hot acidified KMnO4. So the bond will break between the double bond, and then you will notice that both left hand side and right hand side, they have the similar structure. So we will add oxygen at the double bond, and then oxygen that attach with the hydrogen, so become the carboxylic acid. Okay, so another side also the same case. You will have the double bond, and then you have CH3 on the oxygen next to the double bond, oxygen at the hydrogen here. So this is meaning of oxidation. Okay, now let's proceed to tutorial question number 9. Draw the structure. So from here we can see ethanolic KOH and then become alkene. So basically the A should be an haloalkane. So this haloalkane have to consist of 3 carbon because we produce propane. So the structure A can be haloalkane, and then the halogen can be either at first carbon. So since here is given us the side product is KCl, so here definitely we have to use Cl. So we can CH2, CH2, CH3, or you can give the answer CH3, CHCl, CH3. Okay, either one of these. But just recall, reminder must be with the Cl, cannot be the Br, even though Br also is the halogen. Okay, then now we continue with question B, ammonia. So the bond between ammonia will break between hydrogen with the NH2. So break down the bond. Hydrogen always is the most electropositive atom. So it is partially positive. NO2 will be partially negative. So we can see there is one functional group which is the bromine. So this one is nucleophilic substitution. So the bond between carbon and the halogen will be break down, and then the Br will be replaced by the NH2. Okay, so next C, we see there is two halogen over here, and then we add with KCN. So the bond will break between K plus and Cn negative. So just recall back, KCN is the strong nucleophile. Okay, so here the H2C, CH2, the Cl will be replaced by the Cn. Last question. So when we look at this structure, we will notice this is an alcohol, and then this is alkoxy. So basically the alcohol, the bond will break between O and H. So at where we roughly can predict this is the part. Okay, so means that the structure D basically will contain a cyclopropyl with the CH2, and then from here we can see there is the Br, so we know that this one is the CH2Br. Then the H from the alcohol and the Br from the haloalkane will produce this HBr. Now let's proceed to tutorial question, objective part, question number 1. What is the IUPAC name for the following compound? As we still remember, the step 1 we always get the longest carbon chain. So when we look at here, we can see there is a benzene ring over here. So this one here definitely has 6 carbon. So if this as the substitute, we will check this substitute 1, 2, 3, 4, 5, and 6 carbon as well. So we have two parts. One is the benzene ring, and then another straight chain part also consists of 6 carbon. If they have similar longest carbon chain, then second things we are going to check which one will have more substitute. Okay, so if the benzene ring as the parent, so there is only one substitute. However, if this straight chain is the parent, so we can see one substitute is the phenyl, bromo, and chloro. So that's in this case, definitely we are going to use hexane as the parent. Okay, so that is why there is no phenyl as the parent in this benzene as the parent in this case. Okay, then now we need to give the numbering. So if we want to do the numbering as usual, we have two ways. Either we follow the green color one now here, or we follow the red color 1, 2, 3, 4, 5, and 6. So if we use red color, we only until carbon 4 we have substitute, carbon 5 we have substitute, and carbon 6 we have substitute, at where if you total up it equal to 15. If we use green color one here is 1, 2, and 3. So when we total up we will get 6. So again, after we already decide, the next thing we have to give the lowest number to substitute. So in this case, we're going to follow the green color one. So the first substituent at here is known as phenyl. Second is bromo. And then the third one is the chloro. So after we decide the number, so next one we are going to follow the alphabetical order. So P, B, and C. So B comes first, 2 bromo, 3 chloro, 1 phenyl-hexane. So the correct answer is A. The correct answer is B. Question number 2. Which of the following is primary haloalkane? So basically, if you want to identify primary haloalkane, means that you need to know which one is the primary carbon. Okay, so we go through one by one. A, CH3, CHBr, CH3. So this carbon that attached to the Br consists bonded to 2 carbon, so this is secondary haloalkane. For the structure B, CH3, CH, CH2Br, CH3. So this Br is bonded to, if I expand the structure of the hydrogen here, means that one bond to Br, another 2 bond is to the hydrogen. So only bonded to 1 carbon. So this is primary haloalkane. So the answer is B. Okay, so for the C, when you can see this C6H5, at where the number of carbon and hydrogen almost the same and is more or equal than 6, especially for the carbon. So we know that there is a benzene ring. So basically, this is the structure for C, a benzene ring, and then attached to a Cr. So this one we make. This one we don't need to classify because it is a double bond. So we will not classify sp2 carbon. Donkey, the structure of donkey, CH3, CH2, Cl, Cl, and CH3. So this carbon bonded to 1 carbon, 2 carbon. So also we'll consider as secondary. So that's why the answer is B. Tutorial question number 3. When a alkene react with HBr, we are going to follow the Markovnikov at where the electrophile, which is the hydrogen, will attach to the carbon with more hydrogen. So it's CH3 and then this one is Br. Okay, and then for the B, this one we haven't learned yet, but I think later in the next topic or next video we will go into we will learn this in chapter alcohol, when the functional group of OH meet with the SOCl2, the product produced will be CH3, CH, CH3, CH2, the OH will be replaced by the Cl. So next one, structure C. This one also we can see that is the double bond, and then bromine also considered as electrophilic addition. So and then supposedly follow Markovnikov rules, but because of bromine is the reagent, the CH2Cl2 is the solvent, so they will not attach to the product side. So it's CH3, CHBr, CHBr, CH3. So last option, donkey. This one is alkene react with, basically if you are the one who suggests the reagent, you supposedly write down hydrogen because hydrogen is the main reagent. The nickel only plays the role as the catalyst. Okay, but in question sometimes they will exchange the position to confuse you. Okay, so when this happens, break the double bond, form 2 new single bond. So both new single bond will bonded to the hydrogen. So basically it's from cyclopentene to produce cyclopentane. So the question is asked us which one cannot produce haloalkane. So the answer definitely is key. Question number 4. How many isomers are possible for dichroropropane? So propane consists of 3 carbon, even though here they didn't, because of here they didn't mention the position of the chloro, so that means you have to use your imagination so that you can predict how many isomers are possible. So as we know, when we have 2 Cl, it can be attached to the different carbon like this. So CH3, it will become CH2. CH and CH3. Then another possibility is CH2Cl and then CH2 and then CH2Cl. Okay, it's 1, 2, 1, 3. And then now we will consider another condition that where is CHCl, both Cl attached to the same carbon, and then CH2CH3. So another possibility is CH3 CClCl, both Cl attached to the second carbon, and then CH3. So all here we are able to draw 4 isomers. Okay, tutorial question number 5. Butanediol acid can be prepared using the following reaction scheme. What is the compound X? Okay, so when we look at here, we can see KCN, ethanol, reflux. So basically, we supposedly have the idea that this CN replace the halogen. So, and then because we have 2 CN here, so means that there must be the compound that we choose supposedly need to have 2 carbon and then with 2 halogen. So there is no doubt the option B is the answer. So and then this one we call it is nitrile. Basically nitrile can undergo 2 reactions. If react with H3O+, this one we call hydrolysis. So we'll produce, since we are using the R over here, so we will use this one R. If hydrolysis will produce benzoic acid, if undergo reduction, lithium aluminum hydride, ether. So for this one, we will have R, C, this one is reduction. Generally, reduction means gain hydrogen. So the carbon will gain 2 hydrogen, and then the nitrogen also will gain 2 hydrogen. So at where this one we are known as it is amino, consists of amino group, and then this COOH consists of carboxyl group. Okay, question number 6, SN1. So SN1 means that only will, in the step 1, only will involve 1 reactant. So and then this reactant basically tend to form carboxyl ion. So if formed to carboxyl ion, tertiary carboxyl ion is the most stable. So if we want the fastest towards the SN1, it supposedly is tertiary haloalkane. So 2-chloropropane, propane 3 carbon, chloro at the second carbon, CH3, CH3. So means this is the secondary, so this is not the answer. 1-chloropropane, so it's primary, also not the answer. 2-chloro, 2-methylpropane, so propane 3 carbon, 2-chloro, 2-methyl. So for this one, C, it is the tertiary haloalkane. So basically the answer is C. So how about the class of the 1-chloro, 2,2-dimethylpropane, 2,2-dimethylpropane, CH3, CH3, and then 1-chloro. So here we have 1-chloro, CH2, CH3. Okay, so this one we will need to have a primary. However, this primary with bulky group. Okay, so this part we consider this part as the bulky group. So basically later it may undergo rearrangement. So and then if primary haloalkane with bulky group, they may undergo rearrangement, but because of rearrangement to produce tertiary carbocation ion. However, the question here is asked which one is faster. So definitely the answer is still C, because for the option C, the carbocation ion is tertiary, no need to undergo rearrangement. So the time will be shorter if compared to the D, even though it may rearrange to produce the tertiary carbocation ion. Okay, question number 7. From the haloalkane here, we know that this carbon is bonded to 1, 2, and 3 carbon. So this is tertiary haloalkane. And then the NH3 is the weak nucleophile because unable to produce the cation and anion. So basically, tertiary haloalkane with weak nucleophile, it tend to undergo SN1. So again, if SN1 means that it will involve one reactant at the step 1 determining step. So that's why and then it is first order reaction. So if you look at option A, first order to Rx, first order to NH3, so involves 2 reactants and is second order. So answer A is out. Option B, even though is 1 reactant, but the order of reaction here, the power is 2. So again, 1 reactant, but it's referred to second order. So answer B also not correct. So C, we have involved 1 reactant and that is first order. So option C is the answer. Option D again involves 2 reactants and then it is second order. So also not the answer. Okay, next question number 8. Which of the following can undergo the hydrolysis as the following step? So we can see here there is step 1, step 2. So again, it is referred to as SN1. Okay, so because we can see in the step 1 there is only involved 1 reactant. Okay, so SN1 is the tertiary haloalkane preference. So when we look at option 1, CH3 have 3, so means that the structure, if you slightly expand, this one will be the option 1, tertiary haloalkane. For this one will be primary, and then for this one, CH3, CH, Br. Okay, it also is considered as primary, not tertiary. So that's why the answer is 1 only. Okay, second last question. Which of the following describe the bimolecular nucleophilic substitution, which actually is referred to as SN2? So SN2 is only 1 step. So there is no rearrangement. So undergo rearrangement is wrong. And then SN2, the most reactive, normally we remember the primary because we always comparing primary, secondary and tertiary. We always ignore the methyl when we do the explanation. Okay, but we know that the position of methyl should be come first and then only primary haloalkane. So option 2 is correct. The reaction is first order with respect for each alkyl halide and nucleophilic and nucleophile. Yes, so means that first order to alkyl halide and then first order to the nucleophile. So then end up it will become as the second order SN2. So option 3 also correct. Last question, objective question number 10. Which of the following you will obtain if bromoethane is refluxed with alcoholic sodium hydroxide? Okay, so as we know, we have NaOH aqueous and also NaOH ethanol. Okay, for the haloalkane. So maybe you can do a remark here. If haloalkane react with NaOH, ethanol, heat. So basically, this one we learn in chapter alkene. The haloalkane will become carbon-carbon double bond. If the haloalkane react with NaOH aqueous, so basically is the OH will undergo nucleophilic substitution. The halogen will replaced by the alcohol. Okay, so we remark over here as well. This one is the type of reaction is elimination. If haloalkane react with NaOH is nucleophilic substitution. So alcoholic refer to ethanol. So that's why from here we know that alkene will be produced. So the option 1 is the answer.